Welcome everyone. I'm Bené Duncan with Western Water Assessment at the University of Colorado Boulder. And we just want to thank you for making time in your schedules to join us for this webinar, which is the third in a series exploring the recently released report called Colorado River Basin Climate and Hydrology State of the Science. The first two webinars are available on the Western Water Assessment website, so you're welcome to watch the recordings there. For today, we'll have a presentation of about 45 minutes, and then we'll use the remaining time for questions. This webinar is being recorded, and the video will be available on our website later, and we'll be sure to share that link with you after the webinar. But for your reference, it's wwa.colorado.edu. Before we get started, I just wanted to share a bit about Western Water Assessment for those of you who haven't worked with us in the past. So Western Water Assessment is an applied research program that addresses societal vulnerabilities to climate variability and climate change, particularly those related to water resources. And while we're based in Boulder, Colorado and Salt Lake City, Utah, we work across the Intermountain West, which includes Colorado, Utah, and Wyoming. Western Water Assessment is one of 11 teams in the NOAA Regional Integrated Sciences and Assessments, or RISA program. And during today's presentation, you can ask questions with the Q&A window. And so look for that button that says Q&A and feel free to enter your questions there. We'll save any questions that come in during the presentation, and then we'll answer as many of them as possible during the Q&A period. So for now, I'd like to introduce Liz Payton and Jeff Lukas, who are the co-lead authors and editors of the report. Liz is going to start us off, and then Jeff will join in.
Thanks, Bené. I'll provide just a bit of background on the report before Jeff launches into his presentation. The past decade has seen a wave of new research relevant to the Colorado River Basin. The increasing complexity of data and models, combined with the uncertain hydroclimate and with upcoming negotiations in the basin, led a consortium of water providers to seek a synthesis report of the state of the science of the climate and hydrology in the basin. That consortium approached Western Water Assessment in the spring of 2018 to write that report. These are the entities who made up that consortium and sponsored the report: the Bureau of Reclamation, water resources agencies from the 7 basin states, plus several major municipal water utilities and water districts that rely on water from the basin. We also received substantial technical assistance from NOAA's Colorado Basin River Forecast Center and the USGS. The organization of the report generally follows the flow of information that supports management and planning of water supply. The report has 11 chapters contained in 4 volumes. Chapter 2 describes our current understanding of the basin's climate and hydrology and is the foundation for scientific and technical progress in the other areas described in the report, and is the focus of today's presentation. And I'll hand it off to Jeff now.
Great, thanks, Liz. So our understanding of the processes, patterns, and variability in the Colorado River Basin hydroclimate is based on the observational data that we described in the previous webinar. Our modeling and forecast tools also shape the ever-evolving understanding. And then as we get a clearer picture of the basin, we can use that picture to enhance and refine our observational platforms, as well as those modeling and forecast tools. While the metaphor of picture that I just used implies a static snapshot, the reality of climate change and other ongoing physical changes to the basin means that we need to be thinking in 4 dimensions: the 2-dimensional coordinate space, then the variable that we're interested in, and time. So within its 240,000 square miles, the Colorado River Basin has an extraordinary diversity of hydroclimate conditions, driven mainly by the complex topography and resulting gradients in elevation. Due to elevationally driven lapse rates in both temperature and precipitation, the underlying topography is clearly seen in these maps of average annual temperature and average annual precipitation. Note especially the darker blue shades at right, indicating the very high precipitation in the mountain headwaters areas, over 40 inches. And these areas also have the coolest temperatures. There is also a broader temperature gradient that is driven by latitude, wherein the lower basin is warmer than the upper basin at the same elevations. As a note, these and subsequent climate and hydrology maps show data from the gridded 4-kilometer LIVNA version 2 dataset, as discussed in our previous webinar. In the slide we just saw, basin-wide precipitation is concentrated in the higher elevation headwaters. As that precipitation is translated into runoff, the difference between these wetter and cooler headwaters and the rest of the basin becomes even more profound. Very little runoff comes from these non-headwaters areas shown in white in the map at right. Basically any area that receives less than 20 inches of precipitation annually. So fully 85% of the basin-wide runoff comes from only 15% of the land area. And most of those high runoff headwaters areas are in the upper basin, with lower basin runoff coming mainly from the Mogollon Rim in Arizona. Looking at runoff efficiency, that fraction of the precipitation in each of these 4-kilometer grid boxes. Sorry, was there a question? Looking at runoff efficiency, the fraction of precipitation in each 4-kilometer grid box that becomes runoff gives us a similar view. It also makes clear that evapotranspiration losses dominate the water budget across the basin. The vast majority of the basin has runoff efficiencies below 5% and even 1%, meaning that virtually all precipitation goes back up into the atmosphere. Runoff efficiency generally increases with elevation as the climate is wetter and cooler, but even in the highest elevation headwaters in western Colorado, about half of the precipitation still goes back up as evapotranspiration. Overall, the runoff efficiency of the Colorado River Basin is about 10%. This is comparable to the basin-wide runoff efficiency for the Upper Missouri Basin, but much lower than for the Columbia Basin and the basins fed by the Sierra Nevada. They have runoff efficiencies of around 40 to 50%. Importantly, basins with low runoff efficiency are more sensitive to variability and trends in both temperature and precipitation. The concentration of highly productive headwaters in the upper basin, especially in western Colorado, means that the upper basin accounts for, on average, a little over 90% of the total naturalized basin stream flow as measured at Imperial Dam. Among the 3 major subbasins of the upper basin, the Colorado, measured at Cisco, accounts for the largest fraction of the flow at Imperial, over 40%, with the Green River Basin somewhat behind and the San Juan a distant third. The inflows in the lower basin between Powell and Meade are about 8% of the flow at Imperial on average. But note that these proportions can vary significantly in a given water year depending on which parts of the basin were favored by the winter storm tracks. For example, for the 2020 water year, for which upper basin flows have been well below normal overall, the Green produced a higher share than its average, the San Juan a lower share, and the Colorado headwaters close to its average. I said that the broad spatial patterns in hydroclimate in the basin result from topography. It would be more accurate to say it's how that topography interacts with the dynamic motions of the atmosphere over the basin, including upper level winds, storm tracks, and convergence of air masses. These atmospheric dynamics and their moisture sources evolve seasonally, creating overall patterns of seasonality in precipitation across the basin. Throughout the cool season, the primary moisture source for precipitation over the entire basin is the Pacific Ocean. Click, please. In the fall, the westerly winds strengthen and the polar jet stream shifts southward. Mid-latitude cyclonic storms preferentially form along the jet stream's path and then tend to follow that path eastward. Thus, we call it the storm track. The dashed lines here represent 3 typical storm tracks, but there are many variants of these. The position and the activity of the storm track from October through May is the critical climatic driver of annual precipitation in the basin's headwaters and thus of annual runoff. In the winter, the mid-latitude storm track often splits, especially in El Niño years, and storms that follow the southern track will mainly impact the Mogollon Rim and other lower basin headwaters. Atmospheric rivers often accompany landfalling Pacific storms on these more southerly tracks. Each year, several of these atmospheric river events penetrate far enough inland to greatly enhance storm precipitation totals for the lower basin and the southern parts of the upper basin. In spring, Pacific storms affecting the upper basin become less frequent as the westerly winds begin to weaken and shift northward, but each storm carries more moisture due to the warmer air. In the lower basin, the storm tracks are still active, but the storms carry little precipitation compared to the winter months. The Gulf of Mexico becomes a secondary moisture source for the storms as they bring precipitation to the far eastern portions of the basin. During spring and also summer, a sizable fraction of precipitation across the basin is recycled, as indicated by the circular arrow. And so it comes from moisture that has evaporated from the land surface rather than directly from the oceans. June is a transitional month in which the cool season dynamics have largely diminished and the summer dynamics are not fully established. Thus, on average, it is the driest month in virtually all parts of the basin, but especially the lower basin. In the summer, late summer and early fall, intense heating of the land surface brings the North American monsoon, the persistent intrusion of subtropical moisture from the Gulf of California that kicks off widespread thunderstorms over the lower basin and the southern parts of the upper basin. Like in the spring, moisture from the Gulf of Mexico also flows into the eastern portions of the basin to feed more convective activity. Also in this period into October, infrequent landfalls of Pacific tropical cyclones from the Gulf of California can bring moisture and flooding to the lower basin. So like the other large basins of the Mountain West, the Colorado River has a snowmelt-driven hydrology. Click, please. In those high elevation, high precipitation headwaters, most of the annual precipitation falls as snow and accumulates in seasonal snowpacks. Basin-wide, precipitation that falls as snow is twice as likely to become runoff as precipitation that falls as rain. This disparity is mainly because snow tends to fall where and when temperatures are cooler, and so evaporation is less. It also helps when snow falls upon an already existing snowpack rather than on the ground, where it's also more susceptible to evaporation. The upshot is that almost 3/4 of annual runoff in the upper basin comes from snow, even though snow is less than half of all annual precipitation. This tight linkage between snow and runoff is even clearer when we compare the maps of average April 1 snow water equivalent at left with annual runoff on the right. Those areas that consistently accumulate a snowpack of a few inches or more are also those that contribute almost all of the runoff across the basin. Note though that the April 1 time slice shown here underrepresents the snowpack in the lower basin, which peaks closer to March 1st. I think we're all familiar with the general seasonal curve or trajectory of the snowpack, but there are some features worth examining in detail. Here we see a composite curve of snow water equivalent from the 30 or so snowtell sites in the Colorado headwaters above Cameo. The colored shading depicts the range of snowpack conditions over the 40-year snowtell record, and the green line is the 1981 to 2010 median. 3 recent years, 2011, 2016, and 2002, are shown separately as examples of high snowpack, near normal, and low snowpack years. Note especially the slope of the spring melt in these curves. Smaller snowpacks tend to have slower daily melt rates, but because their peaks are lower and earlier, they still melt out earlier than in other years. Large snowpacks peak later, but then have generally faster melt rates. Recent studies show that slower melt is less efficient, which further handicaps runoff in the low snowpack years. So snow that falls after a snowpack has peaked in April and May is important to runoff, not just for adding more water to the snowpack, but also for delaying melt until later in the spring, when it is generally faster and more efficient. We saw the reverse of this just this spring in 2020, when record low snowfall in April and May in the basin led to an early peak and melt initiation, and likely to less efficient runoff as well. So we've heard a lot about dust on snow in the last several years, and likely seen it ourselves. There's always been a low-level dust on snow phenomenon in the Colorado River Basin and most of the interior West. But pervasive human disturbance of soil crusts in the Colorado Plateau and other dust source areas began in the mid-1800s. And in the past several decades, or actually few decades, soil disturbance, vegetation loss, and dust mobility have further increased. This has ramped up the frequency and severity of individual dust on snow events and their aggregate impact on hydrology. In the headwaters of the most affected basins, such as the San Juan and Uncompahgre, moderately dusty years, which are basically the new normal, are estimated to cause snowmelt and the peak runoff to occur about 3 weeks earlier compared to the pre-1800 dust levels. The extreme dust loading that occurred in 2009, 2010, and 2013 pushes melt and runoff 6 weeks earlier than in the pre-1800s hydrology. Regardless of the size of the snowpack and how much the melt is enhanced by dust in a particular year, the eventual melt out of the snowpack and its translation to runoff creates the familiar April through July pulse in the annual hydrograph. For the upper basin as a whole, about 80% of the annual runoff volume comes in that 4-month period, with an even higher proportion in the highest flow years like 1984. The shape of each year's hydrograph is contingent on the size of the basin snowpack at peak, as well as the additional spring and summer precipitation that comes that year. This plot also makes clear the enormous variation in annual volumes, about 5-fold between the highest and lowest flow years. While the size of the snowpack and the size of that year's runoff volume are clearly tightly linked, it doesn't mean that all or even most of the water in the channel during that spring peak actually came from that year's snowmelt running off on the surface, as shown in the schematic at left, representing an older, probably more intuitive view. In the last several years, a new view of the translation of snowmelt to streamflow in the upper basin has emerged from studies using isotopic tracers and hydrologic models. These studies highlight the important role of soil moisture and shallow groundwater. They indicate that much of the snowmelt in headwaters catchments infiltrates the soil and becomes new groundwater. Stored groundwater from previous year's snowmelt is then displaced by this volume of new groundwater, and a roughly proportional amount is discharged to the stream channel. Here we can see that the involvement of subsurface processes in the upper basin runoff does not much affect the tight linkage between the variations over time in water year precipitation in the lighter blue and in water year streamflow in the darker blue. Statistically, about 70% of the variance in streamflow, or an R squared over 0.8, is explained by precipitation alone. But if we examine the vertical scales, we see a doubling of precipitation is associated with about a quadrupling in runoff. This is because high runoff years not only have greater precipitation, but greater runoff efficiency due to generally cooler temperatures, cloudier conditions, later and faster snowmelt, and a shorter growing season for plants that would otherwise take up and release moisture. While the upper basin hydrology is variable from year to year, it is not as unusual in that regard as we might think. The overall coefficient of variation in streamflow, the ratio of the standard deviation to the mean, is around 0.3. This is very similar to the median of over 1,000 rivers found in a global database. Streamflow variability in the lower basin is much higher than in the upper basin, about 0.6 to 0.8. Given the enormous reservoir storage capacity in the basin, decadal scale variability is as important to water supply and its management as the interannual variability. In green, we see the 10-year running average of the natural streamflow at Lees Ferry has varied by about plus and minus 20% from the long-term mean, from about 18 million acre feet down to 12 million acre feet. The dotted purple line shows a 9-year Gaussian weighted filter, which emphasizes the middle values in the decadal period. It shows that in the last 40 years, a decadal signal has apparently emerged, but we'll return to that a little later. We can use tree ring records to extend our roughly century-long gauge perspective of upper basin streamflow variability to over 1,000 years, here using the Miko et al. 2007 reconstruction of Lees Ferry. Here we see that the absolute range of decadal variability in this longer window is not much greater than that which occurred after 1900. But in this longer window, we have a greater variety of flow sequences, including, most critically, multi-decadal dry periods, worse and longer lasting than any recent ones, including a 60-year period in the mid-1100s, in which flows averaged just above 13 million acre feet. This is roughly equivalent to the most recent 30 years of hydrology occurring twice in a row, but with even fewer high flow years to break up the monotony of mediocre to poor years. From this much larger sample of the basin's hydroclimatic behavior, we find that decadal scale oscillations like the one which apparently emerged after 1980 have only occurred intermittently for no more than 30 to 40 years at a time. Multi-decadal oscillations with wavelengths between 20 to 80 years are also present intermittently. So the regular cycles that may periodically manifest in the statistics of basin runoff do not seem to be consistent enough to give us much predictive capability from those cycles alone. But how about the climate phenomena that appear to underlie at least some of the global and regional climate variability? The enormous heat storage capacity of the oceans and their slow movement leads to patterns or modes of climate variability that play out over months to years to decades. Here we see 4 of the lower frequency modes whose variations manifest over several years to several decades. We have El Niño Southern Oscillation, or ENSO, the Pacific Decadal Oscillation, or PDO, Atlantic Multi-Decadal Oscillation, or AMO, and the Quasi-Decadal Oscillation in the Pacific, or QDO. For many parts of the world, there are strong tendencies towards weather and climate anomalies that are associated with these modes. Knowing which phase of the pattern you are in can give you at least some predictability even if the timing of the changes in this mode are not regular. We can see this especially with ENSO. The El Niño Southern Oscillation, or ENSO, is globally the most important pattern of interannual climate variability. ENSO involves massive transfers of energy between the tropical Pacific Ocean and the overlying atmosphere. These energy flows influence the atmospheric circulation well beyond the tropics, creating what we call teleconnections. Much of the skill in seasonal climate forecasting around the world is derived from the current or expected ENSO phase. Once an El Niño or La Niña event is established, it tends to persist into the following year. Thus, ENSO events impart some memory and seasonal predictability to the global climate system. In this chart here, we see the irregular 2 to 7 year oscillation between the warm phase El Niño events in red spiking up past the dashed red threshold and the cold phase La Niña events spiking down beyond the dashed blue threshold. The most recent super El Niño that occurred in 2016 is at the far right. The ripple effects of ENSO events include changes in the position of the jet stream and storm tracks over North America, and consequently areas that tend to be wetter or drier. During El Niño events, the dominant cool season storm track tends to be in a southerly position such that the Southwest, including the lower basin, has higher than normal precipitation on average, while the Pacific Northwest is drier than normal. La Niña events, conversely, see a strengthening of the normal winter pattern in which storm tracks are more northerly, and so the Southwest tends to be drier than normal during La Niña. Note that these schematics and my explanation indicate general tendencies, not destiny. Some ENSO events do not play out this way. This map looks in a little more detail at the basin. It shows the correlation of an ENSO index with October to March precipitation over the basin, thus the general pattern of ENSO influence on cool season precipitation and snowpack. There are moderately strong correlations shown in yellow and orange across the lower basin into southern Utah and the San Juans, indicating that La Niña events are associated with drier conditions and El Niño events are associated with wetter conditions in these areas. Shown in blue, the opposite signal, though not as strong, can be seen in portions of the headwaters of the upper basin in northern Wyoming and in north central Colorado. So La Niña tends wetter and El Niño tends drier. But across the upper basin as a whole, these two tendencies cancel out to some degree. This means that when we look at naturalized annual flows for Lees Ferry over the past 40 years, split among El Niño, La Niña, and ENSO neutral cases, we really don't see meaningful differences in the average or median flow among the three phases. But at the more important lower ends of the distributions of streamflow, it is interesting to see that no very low flows below about 10 million acre feet have occurred during El Niño years since 1980. On the other hand, La Niña does not appear to be associated with an enhanced risk of these flows either, compared to ENSO neutral years. So the implications for basin water supply of the La Niña event that just emerged in the last few months is mixed. During La Niñas, historically, there is a clear tendency for the lower basin to have drier, cool seasons. But for the overall inflows to Powell from the upper basin, there is not a clear signal, though the upper Green and the Yampa basin specifically tend wetter during La Niña. So ENSO gives us some predictability for the lower basin, but not much for the upper basin as a whole. What about the other modes of variability? Several promising studies in the 2000s on the PDO, AMO, and other oscillations raised hopes that using these climate modes would lead to skillful seasonal to multi-year hydroclimate forecasts for the upper basin. Since then, a more complicated and perhaps sober reality has emerged. PDO and AMO are now seen more as statistical simplifications of multiple underlying ocean atmosphere dynamics, rather than being coherent physical phenomena in their own right, which might impart consistent predictability. And relationships that are found between any climate mode and Western US climate during the last century or parts thereof may not be representative of past or future relationships, given the limited number of cases to draw from. So the search for new modes and teleconnections continues in the research community, and efforts to extract more predictive skill from these known modes of variability will continue. However, skill at seasonal and longer timescales specifically derived from these modes of variability may have a lower ceiling than both researchers and water managers would like. And multi-year droughts, which are the events that we are most concerned about with respect to water supply, appear to be quite eclectic in their origins. An analysis of 6 upper basin droughts from the 1930s through the 2000s showed that these past droughts have emerged and persisted through a variety of modes and phases of climate variability, including ENSO. Even if multi-year droughts have had different underlying climatic causes, they all have big impacts on basin water supply. Here is a reclamation analysis of such droughts according to their cumulative streamflow deficit at Lees Ferry. They defined a drought year as being a two-year average flow, less than 15 million acre feet to account for the effect of storage. By this measure, the most severe drought in the observed record was from 2000 to 2005, with a cumulative deficit of 24 million acre feet over 6 years, exceeding the 7-year droughts in the 1930s and the 1960s. There was another 6-year drought from 2012 to 2017 in this chart, but I've updated it to show that this drought has persisted, with the cumulative deficit growing from 13 to 18 million acre feet due to the dry years in 2018 and 2020. And this is now the longest drought by this measure in the observed record, 9 years. So the period since 2000 is unusual in having 2 multi-year droughts by this measure and a total streamflow deficit of over 40 million acre feet between the 2 droughts. In addition to the historic variability in the basin, we also know that the Earth's climate system has been undergoing systemic changes to human emissions of greenhouse gases, as well as other alterations of the atmospheric and land surface. So what trends in climate hydrology can we see in the last several decades in the basin, and are they plausibly linked to the global changes? The most prominent hydroclimatic trend in the basin has been a substantial and statistically significant warming trend of about 2 degrees Fahrenheit over the past 40 years. Over the basin and in the upper and lower basins separately, 2009 to 2018 was the warmest 10-year period in the record, and 2017 was the warmest single year. While this upward trend over the last several decades has included both warmer and cooler years, every year since 1994 has been warmer than the 1970 to 1999 average. So far, 2020 has been a top 10 warmest calendar year in the basin, with August 2020 being, in fact, the very hottest August on record by a wide margin. So after a bit of a reprieve in the relatively cool 2019, the basin is very much back on the warming track. And this warming trend shown here for the basin mirrors the persistent warming trends seen over the same time period in the Western US, North America, and the entire globe. At the global scale, it is extremely likely that human influence has been the dominant cause of the observed warming. For the Western US, human influence has been detected in the warming as well. As shown previously, observed water year precipitation for the basin is far more variable on interannual timescales than temperature. And while a straight line trend over the 1980 to 2019 period for the upper basin, shown here, does indicate lower average annual precipitation in more recent years, this declining trend is not statistically significant relative to the year-to-year variability. New analyses using global climate models suggest that human-caused climate change is exerting a long-term tendency towards reduced precipitation in the region that includes the Colorado River Basin, but this tendency, this forced tendency, is relatively small. So it is likely that much or most of the downward statistical trend in precipitation seen here is due to natural variability, with some contribution from shifts in circulation patterns due to anthropogenic climate change. For snowpack, since the mid-2000s, numerous studies have found pervasive declining trends in April 1 SWE at the snowtel and snow course measurement sites throughout the Western US, including in the Colorado River Basin. Here we see a plot of the basin average April 1 SWE for the upper basin from 1980 to 2020, based on snowtel, on the same horizontal scale as the previous time series plots. We see a declining trend that is of similar magnitude than the one in it's similar magnitude, possibly a little greater than the one in water year precipitation. All of the studies indicate a role for warming temperatures in explaining this declining SWE, though recent precipitation trends appear to be responsible for a large part of the decline, as we might expect. Two studies that analyze gridded snow data sets rather than snowtel and snow course found larger SWE declines than one would infer from the snowtel and snow course sites alone, which indicates that the lower elevation snow below the elevations of the snowtel network has experienced greater changes than higher elevation snow, which we would expect in a warming climate. Given these findings of widespread declines in April 1 SWE, it is unsurprising that these and additional studies since the early 2000s that have examined the timing of snowmelt and runoff in parts or all of the Western US have also found widespread trends towards earlier snowmelt and runoff over the past several decades. In the upper basin, these trends since 1980 are on the order of 1 to 4 weeks earlier. So what about annual streamflow volumes in the upper basin? Clearly, this is the variable that is most directly relevant to basin water management and water use. Annual streamflow also integrates multiple processes and effects that play out over different time scales and spatial scales, which complicates the evaluation of the sources of variability and change. We see a declining trend in Lees Ferry flows over the past 40 years, a little steeper than the declining trends in annual precipitation and snowpack. However, even larger declining trends in Lees Ferry flows were observed over 40-year periods beginning in the 19-teens and ending in the 1950s. So this recent decline is not unprecedented. We need to dig deeper into the evolution of upper basin stream flows vis-a-vis the climate drivers of hydrology than just marking trends on time series plots. Fortunately, in the past decade, there have been at least 10 studies and 1 workshop that have examined the sensitivity of upper basin stream flow to temperature and precipitation changes, allowing attribution of recent trends. These studies have used statistical methods, hydrologic models, and/or global climate models to try to tease apart the different influences on runoff. The consensus of these studies is that a warming of 1 degree Fahrenheit is associated with a 2 to 6% decrease in annual stream flow. The majority of the studies, including the most recent ones, point to values on the higher end of 4 to 5% per degree Fahrenheit being more likely. If we accept this, it would imply that Lees Ferry stream flows have declined 8 to 10% over the last 40 years due to warming temperatures alone. This also means that of the streamflow deficit since 2000 at Lees Ferry and the overall trend since 1980, between 20 to 50% is due to warming alone, with the rest being due to below normal precipitation. Again, the majority of studies point to higher values, closer to 50%. Regardless of the true numbers, the upshot across all these studies is that we are seeing declining runoff efficiency in the upper basin. We're getting less bang for our precipitation buck. Compared to 10 or 20 years ago, we now have a more nuanced understanding of the broad patterns of climate hydrology in the basin, as well as the important details in space and time, including critically the identification and attribution of recent trends. But we still have some challenges and opportunities facing the research and applications communities. And here we focus on understanding the recent trends because of their importance in framing expectations and refining projections of future hydrology in the basin. The first challenge is better quantification of the recent trends in climate hydrology, and especially their spatial variability across the basin. Along with this is better quantification of the roles of the different causal factors, especially for streamflow, and again, the spatial variability in those roles. Many studies have an upper basin-wide approach, looking only or mainly at Lees Ferry flows. And this may mask uncertainties, errors, or counterintuitive findings that get washed out in a basin-wide picture. We should also pay more research attention to the factors influencing lower basin stream flows. The opportunities then include conducting both empirical and modeling analyses of individual subbasins and headwaters catchments to ensure that these findings are consistent with the basin-wide view or otherwise enrich it. Elsewhere in the report, we discuss ongoing and potential improvements in hydrologic modeling, mainly in the context of seasonal water supply forecasting. But improved modeling capacity can also further our general understanding of basin runoff processes. And at multiple spatial scales, empirical and model-based studies tend to be conducted and evaluated separately, and more intercomparisons would be welcome. So a final thought that goes beyond what is written up in the report and in chapter 2. Those of us who are in the Colorado River community, as water managers, water users, researchers, commentators, journalists, become immersed in the idea of Colorado River exceptionalism. And it's the most appropriated, the most litigated, the most relied upon, the most whatever. That the basin is different from all other basins. But in thinking about the climate hydrology of the basin and acting on that knowledge, I think we need to temper that exceptionalism. The Colorado River is really not that different from the other basins of the interior West, especially the ones with which it shares headwaters divides. So the Platte and the Upper Missouri rivers, the Snake River, the Bear River and the Wasatch Front, the Rio Grande, and the Arkansas River. We would benefit, I think, from greater interchange of knowledge and research and intercomparisons of these basins. And maybe we could say more permeability in our mental boundaries of the Colorado River Basin and its hydroclimate. And with that, I'll hand it back to Liz for some brief announcements before the Q&A.
Thanks, Jeff. I'd like to take half a minute to let people know about a special issue of the Journal of the American Water Resources Association. It's an issue commemorating the 25th anniversary of the severe and sustained drought managing the Colorado River system in times of water shortage issue. This anniversary issue will be edited by George Frisbald plus a number of co-editors, including me. And we are encouraging submissions that reflect on the original studies and provide new insights on implications of multi-decadal drought in the Colorado River Basin. Submissions considering the effects on water quality, public health, and vulnerable border and tribal communities are also welcome. We are requesting abstracts and expressions of interest by mid-October. Please consider contributing to this landmark issue by providing your 21st century view of the river. And the link for more information about the special issue and abstracts is in the, I just pasted it in the chat. Thank you. And now, thank you. I'm going to turn it over to Seth Shanahan, the Colorado River Programs Manager for the Southern Nevada Water Authority, to make an announcement. He'd like to invite you to attend some webinars. Go ahead, Seth.
All right, Liz, thank you so much for that intro. First, let me just start by saying I really want to thank Jeff, Liz, Benet, the Western Water team, all of the contributors for the State of the Science report, because you all have produced an exceptional work product. And on behalf of my organization, Southern Nevada Water Authority, and all of our partners of that consortium that you mentioned, Liz, that we refer to as the Colorado River Climate and Hydrology Work Group, we just thought you all did a great job on laying the foundation for so much of the information that's going to be useful to us and others in this basin for years to come. So when we worked through this project and stood it up, we recognized that it wasn't feasible to have every single topic talked about, and at some point you had to stop and say, okay, we're going to summarize what we know as of a certain date, and that there would be things after that date that would be learned that we'd want to be able to share, and as well as other topics that we knew we wanted to talk about in future forums. And so as a continuation of that kind of theme and using the State of the Science as the jumping off point, you can hear Jeff talk about some of those challenges and opportunities that are in the document. And if you get in there, you can see that there are many challenges and there are many opportunities. So the work group that I work with has decided to have a series of webinars. I think that's the going format these days, in what we're calling the 2020 Colorado River Hydrology Research Symposium. This for us is our second symposium like this. The first was in 2017, where we really gathered a bunch of scientists and water users and managers and other folks around the table. So it's a continuation of that same thinking. But at the same time, right now, it's using the State of the Science as that launching off point to investigate and explore future opportunities as they relate to some of this information that you've heard today. So we'd like you to join us, if you can, on October 8th, October 19th, and November 17th for a three-part webinar series where we'll have many different speakers. So we'll probably have 3 to 5 speakers per each session to talk about some of these opportunities from the State of the Science report, some topics, for example, like decision science that weren't addressed at all in the State of the Science report that I think many of us around the basin are interested in learning more about and its usefulness. So we would like to have not only our typical water users as part of our work group, water managers community. That's certainly important for us to get self-educated, but we really want to invite lots of scientists from the community to participate, so you can add in your perspectives in the conversation as well. So you can see in the chat link, Liz has posted the registration link, so you can go there. So that's one place. And then also our project manager for the symposium is Keely Brooks at SNWA, and she's going to go ahead and put her contact information in the chat window as well. So if you have any questions or comments about it, want to learn more, or having any difficulties, please reach out to her. So again, thank you to the Western Water team for this great report and this opportunity for us to continue this conversation. And look forward to seeing and hearing many of you in the next week or a month to come. So thanks so much, Liz.
You're welcome. Thank you.
Thanks, Seth.
Great. Well, thanks so much to Jeff and Liz for this great presentation, and thanks so much to all of you who have already submitted questions through the chat box. Feel free to keep them coming. I know we've got 9 minutes for Q&A, and so I'm gonna transition over to that now. And so Jeff, for one first question, is as the Pacific warms due to global warming, could El Niños become more frequent and more extreme so that they might create a strong signal for precipitation in the Southwest? So any signals, I think, between climate change and El Nino Southern Oscillation?
Yeah, that's a great question. And really what will happen in the tropical Pacific, including the ENSO region, is really important to understanding how things might change in our region. Now, you might think that because El Nino is the warm phase of ENSO, that in a warming climate with overall warmer ocean temperatures, we might be more tipped to El Nino. But that doesn't seem to be the case. And to the extent that the global climate models realistically simulate El Nino, and La Nina, which they do in some ways and not so much in others, we see some of the models, push us towards, a future with more La Nina, some with more enhanced El Nino, and some more or less continuation of current ENSO behavior. That is, the behavior of ENSO is not that strongly coupled to the overall warming. If we did have a future in which ENSO was strongly tipped due to circulation changes and the warming towards one phase or the other, that would have implications for us. But right now, there really isn't consensus from the models or from the underlying physics of those dynamics.
Great, thanks. And I've got two questions related to sublimation and evapotranspiration. So the first question is, does the evapotranspiration term referenced in the presentation include sublimation? And then the second question is there any indication of how sublimation is impacted by warming climate?
That's a fabulous question. And I've honestly seen it both ways in the literature, where sublimation is explicitly included in evapotranspiration. I don't know that I've seen it specifically excluded. It's like a lot of papers don't really isolate sublimation as an important component in the way we're thinking about the overall basin runoff budget in these the graphs and maps that I showed you. It is at least implicitly included. So sublimation of snow, that is snow going directly from solid to vapor form, often in the spring during sunny, windy conditions, is definitely part of ET. As to how it might change in the future, I think it is likely to go in the same direction as ET overall with warming temperatures, that is greater sublimation. Solar radiation and winds have a big, especially winds, have a big influence sublimation a lot, maybe more so than temperature. But I think temperature overall will win out over variability and change in those other factors.
Great, thank you. Let's see, another question is talking about the SWE decline that you spoke about in the presentation. Someone's wondering if it's at all misleading given that the 1980s were an abnormally wet period. So could you talk a little bit more about the SWE decline and how kind of scientists are feeling, how scientists can be confident about that in the data?
Right. So whenever you're drawing a trend line on a very variable, on any time series plot where the metric of interest varies a lot over time, you risk having an end effect because you've either got a higher low at one end and higher low point at the other end. And that's definitely true for these 40-year trend lines that we're drawing on streamflow, snowpack, and annual precipitation. The 1980s was generally wet. Whether it was abnormally wet, sure. But you have to realize that just about any year or period is not normal in the basin. Variability is the norm. So, I'm glad you pointed that out. If you start a trend in the 1980s, it's going to tend to decline just because of that. And I'm not suggesting And I think my explanation indicates that. I'm not suggesting that anytime we have a declining trend that all or even most of that decline is due to some systematic change rather than just natural variability. For SWE specifically, the many studies of April 1 SWE that I referred to looked at trends over different periods, including 60 to 70 years going back to the 1950s, and then our 2014 Climate Change in Colorado report looked back to the 1930s for those basins in Colorado where snow course data was available that far. And you still see declines over these longer periods that kind of, where you're not starting in the 1980s wet period. So I think the overall finding of recent decline is robust to when you start that trend analysis. But you're right, starting in the 1980s does, you could say, enhance that trend versus other periods.
Awesome, thank you. Let's see, we've got another question, which was, can you determine how much of declines in river flows are due to an increase in forest and brush density versus temperature rise and variation in precipitation? Have you seen anything like that, Jeff, that thinks about kind of forest density and brush density versus temperature and precip?
It's often thought about in the reverse. That is, how much does flow change and often increase when you remove vegetation, particularly take off the forest canopy through either intentionally through logging experiments or in the aftermath of fires or pine beetles. In fact, there's a recent, looks like a really nice review report that came out from the USDA Forest Service on that very topic. If we turn it the other way, we know we've seen increasing forest density in at least some forest types, mainly the lower elevation types dominated by ponderosa pine in the western US. And I think it's reasonable to expect, though there isn't much work along these lines, that there has been a runoff decline in smaller watersheds that are entirely or mainly within that ponderosa pine or mixed conifer type at low to mid elevations. However, if we're thinking about the whole Colorado River Basin, and especially the upper basin, the vast majority of our runoff is coming from the lodgepole forest type, the spruce fir forest type, and then non-forest types above tree line. And these forest types have not really been affected systematically by fire exclusion and other management effects over the last century. And so while I can't say it hasn't happened, my understanding of these forest types and where runoff comes from in the basin, a read of the literature says this has been a relatively minor effect, if any, on runoff compared to the systematic effects from warming and the variability of precipitation.
Great, thank you so much. And we are right at noon, and so I think we're out of time today. Thank you so much to everybody for joining today's webinar, and to Liz and Jeff for their great presentation and for answering our questions. Jeff, I know we did a bit of a lightning round, so thanks for making it through as many questions as you did. And remember, everybody, you can download the full report and view other resources on the Western Water Assessment website, including recording of the previous 2 webinars in our State of the Science Report webinar series. We'll also be posting a recording of this webinar there, and we'll be sure to send the link to you all when it is posted. In the meantime, feel free to reach out to us if you want to keep the conversation going. Thanks so much. Have a great day.
Thanks, everybody.
Thank you all.